properties of the dot product. Now we know about the operation called the dot product. It takes in two vectors, multiplies their corresponding components, adds all of those products up, and the result is a scalar. In math, anytime we have a new operation, we like to talk about the properties of that operation. So I have listed on the left side of the screen a few properties of the dot product. The very first one that we see says that the dot product is commutative, which means I can list the product vector u dot vector v, or I could reverse the order vector v dot vector u and get the same result. The second property says that it's distributive over addition. So the dot that I have here is applied to a sum of two vectors. On the right-hand side of the equal sign, it shows that I'm dotting the vector u with each the vector v and the vector w. So I can distribute, essentially, over those parentheses when the two vectors inside the parentheses are being added together. The next property is saying that we can take a scalar, like c, just a regular old number, and we can multiply it to a dot product. And we're showing that you can move that scalar throughout the dot product. So it's commutative with respect to scalar multiplication. I could first compute the dot product, then multiply by c. Or I could multiply c to one of the two vectors, and then do the dot product between the result and the other vector. Or I could have multiplied the scalar to the other vector. So I can do it in any order. And then the last property on the screen says that if you take a vector and you dot it with itself, it's equivalent to the magnitude of that vector being square rooted. So I encourage you to verify any one of these by using the general form of a vector. You could create the vector u using three components or two, u1, u2, u3 if you'd like. Whoops. And then the same for vector v using v1, v2, v3. Apply each of the operations and show that if you had worked it out the way it's written on the left side of an equal sign and you work it out on the right side, that they'd end up matching at the end. Let's practice using some of these properties with some vectors like the vector a and the vector b that we have on the right side of the screen. And then I'm also using a vector c. I know in the properties c was a scalar, but for this activity where we're working with vectors, I'm picking c to be an actual vector. So the first one, it says to compute the dot product between a and b and then multiply that to c. Now I want to play the vector scalar game here. We know that a is a vector. We know that b is a vector. Therefore, we know that this is a dot product between two vectors, which is a scalar. When I take this scalar and multiply it to the other vector c, that would become scalar multiplication. So my answer will come out to be a scalar, just a regular old number, times a vector. So our result should be a vector. Anytime we do a calculation, I highly encourage you to take a moment and think about what the result should be. Do you expect the result to be a scalar? Do you expect the result to be a vector? All right, let's go ahead and do some calculations. The way that this is written says that we ought to compute the dot product between a and b first. So let's go ahead and do that. A dot b looks like the components of a multiplied to the corresponding components of b. So I'll have 1 times 0 plus 2 times 2 plus negative 3 times 4, which works out to be 0 plus 4 minus 12, which leaves us with negative 8 for the scalar portion. And then next it says take that scalar and multiply it to the vector c. So if I take negative 8 and multiply that to the vector c, Then I'm going to multiply the scalar to each component in that vector so that we have negative 40, positive 8, negative 24. So we're still kind of sticking with the order of operations here, working within our parentheses and then moving along. The result is a vector just like we suspected. Let's go down to the next one. This one says 2 times the vector c. 2 is a scalar, c is a vector, and then we want to dot that with a. A scalar times a vector will still result in a vector, so I do have a vector dotted with another vector, which means the result should be a scalar. So let's do the order that it's written in. 2 times the vector c. We'll distribute that product in so that we have 10, negative 2, 6. And then we're going to take that vector and dot it with a. So a is 1, 2, negative 3. And 2 times c was the vector 10, negative 2, 6. We'll multiply those corresponding components and then add the result to get negative 12. We have one last one left. This says take the vector b, find the magnitude, and then square it. Working with vectors and finding their magnitudes, we know that that operation creates a scalar. And if you square a scalar, it doesn't magically turn into a vector, so this one we also expect to be a scalar. If I take b squared, that looks like 0 squared plus 2 squared plus 4 squared, square rooted, and then squared, which we can simplify to be 4 plus 16 inside of the square root, that's squared, or the square root of 20 squared. That square and the square root cancel each other out, leaving behind 20. Now if we wanted to, we could use this shortcut property that says it's the same thing as the dot product between b and b. So that would look like this, where we multiply the corresponding components. So we have 0 times 0 plus 2 times 2 plus 4 times 4, which you'll notice is almost exactly what we had inside of our square root. And if we had canceled off our square and our square root right away in step 1, it would look just like that. All right, so there's just some examples of the properties of the dot product and how to use them. We started this section talking about an application that required a computation, which we found and called the dot product. And that process was all with the goal of finding theta between two angles. So we were trying to find the angle between two vectors. And we ended up finding a relationship that looked a lot like this. The dot product on the left side of the equal sign, the magnitude of the two vectors times cosine of the angle between them on the right-hand side. But we stopped there and got distracted by this new operation. We said, wow, that dot product, that's so cool, we should talk about it. So we did. But let's bring ourselves back to the topic of finding the angle between two vectors, because that was our goal in this section to begin with. Now I'm listing off two vectors. I'm using the standard unit vector notation here, and I'd like to find the angle between those two vectors. Now personally, I like to rewrite this equation so that it's already solved for theta. So to do that, I need to divide off the two magnitudes. That would leave me with u dot v divided by the magnitude of u times the magnitude of v. And that would be equal to cosine theta, but to solve it for theta, I would use cosine inverse on this ratio. So to find the angle between these two vectors, maybe I'll call this vector u and this vector v. All I need to do is compute the dot product between them, then the magnitude of each one, And then I'll plug that ratio into cosine inverse to calculate the angle. So let's start with the dot product. I'll multiply corresponding components. Now, in the standard unit vector notation, I'm multiplying the coefficients on each of those unit vectors. So the u and the v, the I components, would look like 1 times 2. The j components would look like 1 times -1. And the k components would look like 1 times -3. We add all of these together, we get a -2 for the dot product. Now we can do the magnitudes. For the magnitude of u, I have 1 squared plus 1 squared plus 1 squared. That works out to be √3. For the magnitude of v, we have 2 squared plus -1 squared plus -3 squared, all square rooted. That works out to be √14. Now I'm ready to plug each of these pieces into the equation that we developed using the law of cosines. So we'll have theta is equal to cosine inverse of 2 over the product √3, √14. And at this point, we would go to our calculator if we wanted an approximate value. This doesn't work out to be a perfect angle that has an exact value, like some of our angles in quadrant 1, like 45-degree angle or 30-degree angle. So we would need to think about the application to decide, do we need our answer of theta to be an approximate in radians, or do we need our answer theta to be an approximate in degrees? Whichever one you need, you would set your calculator to that mode, then you would type cosine inverse of that ratio into your calculator. Just for the sake of trying it out, let's calculate it both ways. So if I were to do this in degrees, I would do cosine inverse of 2 over √3 times √14. So in degrees, theta is approximately equal to 72.02. And if I were to switch my mode into radians, theta would be approximately equal to 1.26 radians. So depending on the application, you would need to pick the appropriate mode for your calculator. Let's try another example of finding the angle between two vectors, this time using component form of two vectors. So again, I need to calculate the dot product and the magnitude of each angle. So we're going to do, of each vector. So we're going to do that first. So I'll call the first vector u and the second vector v. Calculate that dot product. Get -4 minus 20 plus 24. That dot product comes out to be 0. And then I can do the magnitude of u, which would be 2 squared plus 5 squared plus 6 squared, square root that. Get square root 65. And we'll calculate magnitude v. Plug all three of these values that we just found into the ratio for cosine inverse. Now we should probably simplify this ratio before typing it into a calculator because it's unnecessary. 0 divided by any non-zero number is just 0. So we're really looking at cosine inverse of 0. And if you think of the unit circle, cosine of an angle only spits out 0 in two places. It spits out 0 at pi over 2 and 3 pi over 2. Now cosine inverse is only defined on a certain interval of values, and that's from negative pi to pi over 2. That's not true. Cosine inverse is defined from 0 to pi. Sorry for that, I misspoke. So when we type cosine inverse 0 into our calculator, it will spit out an angle between 0 and pi, or 0 and 180 degrees. The only answer for this within that interval would be pi over 2. So in this case, the angle between the two vectors is a 90-degree angle, or it is pi over 2. We don't need a calculator to approximate that because we have the exact answers for that expression. Finding the angle between two vectors, there's only so many cases that we can have. So there's different types of angles. There's an acute angle, which is so cute because it's less than 90 degrees. We have an obtuse angle. Those angles are greater than 90 degrees. We have a straight angle, which is exactly equal to 180. Or we have a right angle, which is exactly equal to 90 degrees. So when we look at two vectors, we have these 4 scenarios. It's either an acute angle, an obtuse angle, a straight angle, or a right angle at 90 degrees. So looking at our pictures here, let's go ahead and label each scenario. The angle between these two vectors looks acute. The angle between these looks like it's greater than 90 degrees, so that would be obtuse. This angle looks like it's perfectly square, which means that's a right angle. The angle between these two vectors looks like it makes a perfect 180 degrees, and in this drawing you can really see why we call it a straight angle, because the two vectors together make a perfect straight line. Ooh, we have one case that I don't have a label for, and this one's often confusing for many people. The vectors are parallel to each other. They're pointing exactly in the same direction, which means they do not have an angle between them, or rather there's a 0-degree angle between them. If we want to determine whether two vectors are orthogonal, meaning if we want to know whether or not the angle between two vectors is 90 degrees, we can use that formula to calculate the angle between them. So theta is equal to cosine inverse of the ratio, the dot product over the magnitude of each vector. Now, the two vectors we have are called P and Q, so we can easily adapt this to be for the two vectors P and Q. So we need P dot Q for our numerator. We also need magnitude P times magnitude Q. So let's calculate each of those. The dot product between P and Q, that looks like 1 times 10 plus 0 times 3 plus negative 2 times 5. That would be 10 plus 0 minus 10. The dot product there is 0. The magnitude of P would look like this expression. And oops, almost forgot the square on my 5. Simplify that, we get the square root of 26. Magnitude Q, simplify that. Let's go ahead and take a couple of steps here. All right, we have the 3 values. We're ready to plug it in. 0 on top for the numerator, root 26 times root 113 in the denominator. Just like in the last problem, if we can simplify what's inside the parentheses, we ought to. Because we have 0 on top and a non-zero number on bottom, that fraction reduces to be 0. And just like the last case, cosine inverse of 0, we said theta would be equal to 90 degrees. Now, we did the entire calculation, but there's one thing that's causing us to have cosine inverse equals 90 degrees, and that's the fact that the numerator was 0. If the numerator is 0, then we're looking at cosine inverse of 0. The numerator was 0 because the dot product was 0. And so that's going to be our shortcut. If we ever want to know whether or not two vectors are perpendicular, orthogonal, or normal, whatever words you want to use, we only need to check the dot product between them. And this is a definition here, so it works forwards and backwards. If I tell you that u and v are vectors that are orthogonal, then you are guaranteed that the dot product between them is 0. And vice versa, if I tell you that vector u dotted with vector v is equal to 0, then you know that u and v must be orthogonal vectors. So it works forwards and backwards. We're going to look at a few special angles next, and we're specifically going to look at a vector like this vector v, and the angles that it forms with each of the standard unit vectors, I hat, j hat, and k hat. Remember, the unit vector I hat is the same thing as the vector 1, 0, 0. J hat is the same thing as 0, 1, 0, and k hat is the same thing as 0, 0, 1. So we're essentially doing that calculation for theta using v and each one of these standard unit vectors. So let's go for it. Starting with alpha, we're going to, instead of calling them all theta, we're going to name them different Greek letters. So for the first angle, alpha is going to be the angle between v and the unit vector I. So alpha would be cosine inverse of the dot product between v and I. Now, if I look at the vector v and I look at the vector I, when I go to compute the dot product, I'm going to multiply a bunch of zeros. So it's really just the 1 in the x position from the I hat unit vector times the 2 in the x position from the v vector. So that dot product is 2. Quick calculation. We could write it out and show that we're multiplying a bunch of terms to zeros, but if we see that quick calculation, then maybe we don't waste our time writing it out. Okay, next we need to do the magnitudes. So let's calculate the magnitude of v. Four plus 9 plus 9. I know 9 plus 9 is 18, not 19. And then 4 plus 18 would be 22, so we have root 22. And then we also need the magnitude of the unit vector I, but remember, by definition, a unit vector has a magnitude of 1. So I could calculate it, but I could easily remember the definition to say the unit vector I has a magnitude of 1. So then in my denominator, I'll have root 22 times 1, and that would be the measure for alpha. This is the angle between the vector v and the standard unit vector I hat. Now, if this simplifies, then we should simplify it. And the best we could do is get rid of the 1. But 2 over root 22 doesn't get simpler, and even if it did, cosine inverse of that value is an approximation on our calculator. So let's go ahead and keep it like this for an exact answer. And let's continue on finding next the angle beta. So instead of theta, we're calling this one beta, and it would be cosine inverse of the dot product between v and j. Now remember, j has a bunch of zeros in it, so it's really just the product of the y component of j times the y component of v. So our dot product will be 3. And then in the denominator, we need the magnitude of v. Well, we already calculated that to be root 22 times the magnitude of j, which is 1 since it's a unit vector. So this simplifies only again by removing that factor of 1 in the denominator, and we will again leave this because that's the exact form. We have one left to do, and that's the angle gamma. Gamma is the angle between V and the unit vector k. So we'll have cosine inverse. The dot product between V and k is the 1 from the z component of k times the 3 from the z component of V. So we have 3 in our numerator. In the denominator, again, it's root 22 since that's the magnitude of V times the magnitude of a unit vector 1. So we've calculated our 3 angles. And we're going to leave them in exact form again because approximations aren't always better. The 3 angles that we just found, alpha, beta, gamma, they're actually special angles called direction angles. You can see them in the picture on the screen. We have the vector v in gold. We have each of the standard unit vectors in blue. And we have the angles labeled alpha, beta, gamma. Anybody who's taking engineering classes will learn about direction angles in those classes from Svetla Gargova as well. So here's just a sneak peek since we were talking about finding angles. Figured we'd take a minute to find them.